Thank you.
For the introduction. Yeah, so today we are talking about breaking XSS mitigations. So we are Christoph Kotovic and Eduardo Vela and myself. And Eduardo is unfortunately not here today, so we are giving the talk. So I will be giving the first part of the presentation, and Christoph will give the second part of the presentation. So let's see what this is all about. This is about XSS and mitigations. And specifically, we want to bypass XSS mitigations. And here you can see Mr. XSS mitigations trying to mitigate XSSs. And, well, he's not doing very well. So let's talk about XSS mitigations first. So one of the major problems in web security is cross-site scripting. And we have put a lot of effort into cross-site scripting to fix it or to prevent it. And despite of all this effort, XSS is still omnipresent. So as a data point, for example, in the Google Vulnerability Reward Program, XSS makes 70% of all the reported vulnerabilities. And we have literally dozens of people working just on XSS preventions by rewriting applications, by creating auto-escaping templating systems, by creating detectors and scanners, and still we have such a huge number of XSS. So this is really a fundamental problem of the web platform. And that's basically the basic assumption of XSS mitigation techniques. So XSS mitigation techniques say XSS vulnerabilities will always exist. So even if we try very hard, we cannot create an application without an XSS. So let's not only focus on preventing XSS, but let's try to mitigate attacks that results from XSS vulnerabilities. So the attacker model that we will talk about today looks as follows. So you have a website, and as we just learned, at some point you will have an XSS in your website. And there is where the XSS mitigation kicks in, so it tries to prevent the exploitation. So how is this working? So basically, all the XSS mitigations have one main assumptions. They try to identify good and potentially malicious HTML and try to block the malicious ones while allowing the good ones. And today we will look at 4 different mitigation techniques. We will look at web application firewalls, at browser-based cross-site scripting filters, at HTML sanitizers, and the content security policy. And so, for example, web application firewalls and XSS filters try to prevent XSS attacks by blocking maliciously looking requests. So they will look at the request, will see, oh, there's a script tag in there or a JavaScript event handler, so let's just block this request. HTML sanitizers have a different approach. Like you have a piece of HTML that comes from the user and you would like to make sure that the user cannot do anything bad. So you give this to the sanitizer. The sanitizer will parse the HTML and will try to remove all the known bad things or only let through the known good things. And the same is true for the content security policy. So the content security policy tries to identify legitimate scripts and illegitimate scripts by forcing developers to put all the legitimate scripts into separate scripts, and then by whitelisting these scripts. And you have different ways of whitelisting a script, so you can either do that on an origin basis, you can say everything that comes from example.org is trusted, or you can use nonces or hashes. So last year we had a paper where we showed that origin-based whitelists are insecure. So CSP is currently moving to this nonce-based approach, where you say the developer puts every legitimate code into a script, then puts a nonce to the script, and this nonce is a random number that the attacker cannot guess. So when the attacker wants to do an injection, the attacker can create a payload, but cannot outfit the script with the right nonce because it's regenerated at every page load, and it's not known before the page actually loads. So really, the main assumption of XSS mitigations is that you can stop XSS attacks by blocking dangerous tags and dangerous attributes. And what we asked us in this research is this main assumptions of XSS mitigations really true when building a modern application? Not like the classical reflected XSS that we've seen 10 years ago, but really a modern application that makes heavy use of JavaScript libraries and has all the modern stuff that you want to have in an application. And well, the short answer is no, this assumption is not true. That's what we're going to show you in the next 35 to 40 minutes. But in order to do so, I would first like to talk a bit about the basics, about JavaScript frameworks. So the main purpose of a modern JavaScript library is to interact with the DOM. So the goal is to either write to the DOM, to read data from the DOM, to do to react on user interactions and then change the DOM based on the behavior of the user and so on. And the main way of doing so is so-called selectors. So here we see a very simple example. So we see like a custom tag, and it has some ID attributes and class attributes and some attributes. And selectors allow you to query the DOM for these elements. So for example, you can query elements by the name of the tag, you can query them by the ID, by the class, or you can even query the DOM by attributes. You can say, give me all the attributes that have, for example, a data foo attribute. And you can even do more. You can say, give me all the elements that have a data foo attribute that begins with bar, which is the last example in this row. And these selectors come in various flavors, and there are a lot of like alias functions, for example, get element by ID or get element by class name in the DOM that allow you to interact with the DOM. So, but basically, you can use the query selector all function to run all kinds of selectors. And these selectors are really core to all JavaScript libraries. And I guess all of you know the super famous jQuery $function. So jQuery is the fundamental of the web. Almost every website uses it. Almost every framework is based on jQuery. And the core of jQuery is this $function. And actually, it's just a glorified wrapper around query selector all, the function that we've seen in the last example. So the $function accepts an arbitrary selector. This selector then selects elements from the DOM, so you get a set of elements, and then with jQuery you do some actions based on this selector. And selectors come in different kind of flavors. So this is the most famous one. Another example, for example, is the Twitter Bootstrap framework. So Twitter Bootstrap uses what they call a data API or data attributes-based API. So they also use selectors to find all the elements in the DOM that have a certain attribute set. And here we have a tooltip example. So if you want to write a tooltip in the Bootstrap framework, which is like a set of UI components, you just put some data attributes onto your element. For example, you say data toggle equals tooltip, and then there's some userland and Bootstrap code that bootstraps the tooltip functionality, and then Bootstrap will just create this tooltip functionality for this element and render this title tag onto this page. So this is also done by selectors, although you cannot see it from this example. And this is an example I would like to dig into a bit and see how a library would implement such a functionality. And here we can see a simple example of a button. So you see we have a data role attribute that says, hey, I'm a button, and that may be a functionality that enriches the button with some CSS functionality, styles it, does a few crazy JavaScript and CSS magic to it so that it looks nice and behaves nice when you click it or hover over it. And what you see here, we have a data role attribute that says this is a button, and you have a data text attribute that is the text that should be rendered on the button. So how would you go to implement this? So in this case, we just use jQuery, right? And we use selectors over here. We say, hey, as a framework, give me all the things that have this data attribute set on the page. So to turn this into a button. Then you have some magic that turns this into the button, adding styles and other functionality. And then in the end, you take this data text attribute and you just render it as the text of the button. And now I have a question for you. So are there any security issues in this code? Do you think this code is perfectly safe, or are there any issues, especially with keeping mitigations in mind? There's an idea? Yes. So the security problem is here. So in general, in a normal web application or library, this would not be a security issue. This seems like normal code that you see very often. But the problem here is that this data text attribute is actually rendered as HTML. So basically, this code here turns this data text attribute in a magic property that suddenly has the capability of executing arbitrary HTML code. And this is exactly what we call a script gadget. And here you can see an example of how you can exploit a script gadget. So now we have this button functionality. Let's assume we have an XSS, and we have an XSS mitigation. For example, an HTML sanitizer in the page, where you can render some limited HTML. So the sanitizer will block all the script tags and onload tags, but some sanitizers will actually not touch data attributes, because data attributes are just data. They don't execute code by default, right? But now this code down here turns this data attribute in a code execution attribute, basically. So what you can do, for example, to bypass a sanitizer is you just put arbitrary elements here. And what you see here is, for example, a sanitizer bypass. It will probably bypass XSS filters, and this also bypasses the content security policy, because this is the jQuery HTML function and does the magic. But we will see later on. So basically, let's talk about these script gadgets. So to summarize, a script gadget is a piece of legitimate code in your page that can be triggered via an HTML injection. So by injecting some benign looking element, you can execute code in a function that does a certain thing. And what we asked ourselves at first is, are these gadgets common? So do we see a lot of gadgets, or is this just like a weird behavior that no one would use? So what we did is we took 16 modern JavaScript frameworks, so mainly based on popularity and like GitHub likes and usage stats and so on. And we tried to look at them and build applications out of these frameworks. So for each framework, we built an application, and then we added an XSS flow to this application. And then we also set up mitigations for every applications. So we set up 4 different mitigation classes, so CSP, XSS filters, sanitizers, and web application firewalls. And we kind of use the default settings, but we use a kind of different configurations. For example, we set up whitelist-based CSPs, non-spaced CSPs, and for XSS filters, we use different XSS filters, and sanitizers and WASP, we also had different examples. And then we manually analyzed the framework code to look for these gadgets and try to find out how many of them we can find. And this is a sneak peek on the results. So basically, we were able, via these gadgets, to bypass all the tested mitigations and in all the configuration in different frameworks. And what you can see here is, we will dig deeper into these results later on, but what you can see here is, so whitelist and nonces were the strongest ones, but then we can see here unsafe eval is pretty bad in terms of bypassability. Also strict dynamic weakens the policy. And also firewalls and XSS filters and sanitizers, they are not doing very well. So we bypass more than 50% of the different combinations. And this is what we actually found in the framework. So we looked at the framework code, and frameworks have many different kinds of gadgets. And the first things that you see is that frameworks make heavy use of these selectors, as I explained before. So you see document query selector a lot, you see document get element by ID a lot, and so on. So they frequently read data. And what they also do a lot is inner HTML-ing stuff and evaling stuff. So these are the classical DOM XSS things that you might know when testing for DOM XSS. But we also saw that a lot of frameworks do, for example, create script elements based on some user content. And also, interestingly, we saw that there's a lot of JavaScript stuff going on. So we see that a lot of, for example, properties are set on user-controlled data, or functions are called based on user-provided data. And this will be the 2 parts of this talk. So in the first talk, I will talk about these traditional DOM-based gadgets, and in the second part, Christoph will talk about these more JavaScript-like gadgets. And what we found out is that these gadgets that do a certain functionality can be chained together. So you can take different functionalities from different libraries and trigger them individually, and then chain them together to do security-sensitive action, and in the worst case, to trigger arbitrary JavaScript code. And we have a couple of examples. So in the next slide, I will use Knockout as an example, but these examples really work for all the libraries that are out there, and we will see a few more afterwards. So here we have a very simple example of a data binding functionality in Knockout. So we see there's a data bind. You already see it's a data attribute, so it seems to be benign, right? And it has a functionality to just assign this to a value. So let's see what Knockout does in the background. So the first thing that Knockout does, it reads this data bind attributes via this selector. Here you can see the usage of selector, and then it processes it in a way. And the second step, it creates a binding object. And what you can see here, it constructs JavaScript from this binding. And then it puts this JavaScript into a function, and luckily it also executes this function for us. So in this call, we can see here's a binding function, and then it calls it with the node, which is this one. So how can we turn this into an XSS mitigation bypass? So this is the bypass. So what we've seen is that the value that is read from the data bind attribute is put into eval. And there is no validation happening at all that this thing is benign or not. So this is a very simple gadget that, for example, bypasses HTML sanitizers. And probably also XSS filters. Yeah, we see here, so what we bypass with this gadget or variations of it is DOM purifier, all the XSS filters like NoScript, Edge, XSS filters, and the Google Chrome one. And we also bypass mod security with a core rule set configured. So, but we can also turn these knockout gadgets into other things. So as I said, we can have different gadgets in the library and we can chain them together to do the different things. So for example, here we have the same example, but we just use the HTML functionality. And interestingly, what happens here is it reads this value, so the hello world above here reads this, then it processes this and sets this as HTML. And what we see here is that knockout falls back to jQuery when doing so. So there's a combination of libraries in here that are at play. So you can even chain gadgets across libraries. And we've seen that actually a lot. So for example, a lot of libraries make use of jQuery when it is available, or when it's not available, they jump to their own code. Or what we've also seen is polyfills, for example. So the library always checks, is this functionality there? If not, then load a polyfill that does some magic on the HTML. And interestingly, jQuery has a special behavior for script tags, because if you assign script tags to inner HTML, they will not execute. So what's happening here is that we have this HTML, and this node will be passed to the HTML function, and this HTML function will grab for script tags, and whenever there's a script tag, it will just execute it. And it will execute it by creating a script element and writing the code to the script.txt and append it to the DOM. And this, for example, is a CSP strict dynamic bypass, because strict dynamic works that it propagates trust to scripts that are created by trusted script. So this DOM eval is part of jQuery. So probably in your page, jQuery is a trusted script that you whitelisted in CSP. So it will just transfer trust to the newly created script. But this newly created script can come from user input via an XSS. And here we see the full CSP strict dynamic bypass. So we can just put a script tag, arbitrary script tag, it will be executed despite CSP in the page. So let's look at other gadgets. So we call these simple gadgets, and Christoph will later talk about like some more crazy stuff. So we have a couple of examples here. So here we have a strict dynamic bypass in Bootstrap, for example. This is the tooltip functionality that I've showed you before. And interestingly, the tooltip Bootstrap does everything via data attributes. They call it data attributes API. And so here we have a tooltip, and by default, this tooltip is rendered as text. But as the Bootstrap functionality works by data attributes, you can just change the internal configuration of Bootstrap. So you can just add a data minus HTML equals true, which Bootstrap will turn into configuration property, and then it will happily assign this to script, and it will use jQuery, which will create script nodes. So this bypasses CSP strict dynamic. Another example is a bypass for a sanitizer in jQuery mobile. This is an interesting one. This is an ID attribute, and all the sanitizers that we looked at, they happily accept ID attributes. They say, well, ID attribute, what can be bad about an ID attribute? And you often need it, so let it through. The thing here is that jQuery mobile prints a debugging instruction. It says something like, so it creates a new element for this pop-up that it creates here, and it just has a debugging instruction with an HTML comment that said, this is a placeholder for ID X. And it puts it into an HTML comment. So you can just break out of the HTML comment, add a script tag, and the ID attribute magically becomes a script execution attribute. Another example is the closure library. And this is an interesting attack vector because it uses DOM clobbering. So closure loads other JavaScript files, and it uses a base path to do that. And the base path is an internal configuration property that is in the DOM, and actually you can clobber the variable. So what you do is you just inject an A tag, because a toString of an A tag results in the URL, and then you put this as the ID. This overrides the internal closure configuration property, so closure will just will load all the scripts from this URL, relative to this URL. And interestingly, closure creates script tags and appends them to the DOM, so this is again a CSP bypass and also a no-script bypass. Here's another example, bypassing mod security with the core rule set installed in the Dojo toolkit. So here you can just take an arbitrary div tag, and you just put a data attribute and put some type into it to make Bootstrap process it. And then you see this attribute. And this attribute gets put into an eval, I think, eval or function call. So so you can just break out of the current context in this eval and just put an alert here, and it will execute. And mod security will not be able to find this because it will look for script tags and event handlers and so on, and it will have no way to identifying this. Another example is underscore templates. So for example, underscore has a magic functionality to execute scripts. So instead of writing script my script code closing script, you just write smaller than percent and script, and it will eval it. So this is, for example, a CSP unsafe eval bypass. Okay, so these were the simple gadgets. And now we have some more crazy stuff, and I will hand over to Christoph to talk about this.
Right, so yes, the more crazy stuff. Some of the gadgets that we found were in a functionality of a couple of frameworks that have the expression passes. So the more complex frameworks, essentially. And those gadgets turned out to be really powerful in bypassing mitigations. So examples of such frameworks are Aurelia, Angular, Polymer, Reactive, and Vue. All of those use expressions. In the DOM, there's a piece of code that is being evaluated using a custom framework-specific parser that is not based on eval. This is the important part, because, like for example, the Sebastian showed before, one of the expressions in the underscore templates in the percent tags, let's say, and those were simply passed to eval. This is not the ones that we are talking about. So those expressions in those frameworks are being compiled to JavaScript using custom code, custom parsers, ASTs, tokenizers, and all that. However, when those resulting expressions or resulting code is being evaluated, it does operate in the regular JavaScript execution environment in the browsers. So they have the capabilities of touching DOM objects. They have the capabilities of reading or writing attributes. They also hook on native objects or native arrays. So there is a possibility of interacting with the actual DOM on the page, and this is something that we actually wanted from the gadgets. What we found out is, like, with sufficiently complex expression languages, we can run arbitrary JS code and make it XSS mitigation bypass. An obvious example of this is the whole family of AngularJS sandbox bypasses. AngularJS also, behaves like that, right? So AngularJS has a custom-based expression parser. And what most of the sandbox bypasses for AngularJS framework showed throughout last years, I believe, is that you can escape this parser or escape the execution environment. This is virtual sandbox that tries to limit what you can execute from within the expression language into, well, alerting, essentially, right, as a proof of concept. So our research kind of builds upon that, but in a slightly different context. Let's see an example. So, for example, there's Aurelia framework. This is an example expression language expression here. So within this data cell, just output the customer's name, right? So how does Aurelia implement this? Well, it has a couple of gadgets, as we call them, right? So in the expression parser first, when it encounters the dot symbol, so this one from the customer, it creates a new object which is called access member, just so later on it can traverse this object graph and execute those particular members. And when this expression is being evaluated, the access member evaluate property is being called, and in this case it simply returns some property of an object. So in this case there would be an object named customer or representing a customer, and it would have a name property, and calling evaluate function will just return this name, the value of this name property. They also have a function called gadgets in this particular framework. So, for example, you can call a say hello function, which is part of the legitimate Aurelia application code, right? This is not something that we actually inject. And this function does something. It doesn't really matter here. What matters is when Aurelia tries to pass this, it encounters like these open parentheses, and then it creates a call member object, passing all like function name and potential arguments being extracted from here, and so on and so forth. Later on, when this expression is to be evaluated, which usually happens when, well, the template is being rendered, for example, the function So this is supposed to be like the func is supposed to be a reference to the say hello function here. Like again, a piece of legitimate JavaScript code, part of the application using Aurelia framework. And this function is simply being called. Function.apply in JavaScript is just calling a function bound to a given object and with certain arguments being passed. So as you can probably see, those expressions or those gadgets, those snippets of code are pretty benign on their own. Like they only implement the functionality of the framework. However, we can still turn them into arbitrary code execution. How do we do that usually? Well, usually when we start the expression, so expressions are evaluated in a certain context. The context often is some kind of element in the DOM or element in a template within the DOM. And we can traverse that using the property accessors to, from a node to window. You will see an example in a second. And then once we have the reference to the window, we can again abuse this expression language in order to get the reference to the alert function of the window as a proof of concept, right? And then we can abuse the expression language, the function call one, to, well, essentially execute this alert function. And this is how it looks like for Aurelia. So we have, we store the reference to the current node, which is, there's a ref attribute simply. And then we execute this particular expression, right? So this will evaluate to this div element. Then we check the owner document, which will return the document element or the document object. Then we check the default view, which is a reference to the window. Then we just call the alert, essentially. Why is this one interesting? Well, because we essentially, that's like a code reuse attack. So we never actually created a new script element. We never actually created something that was not there before in the DOM or in the execution environment. We reused the functions that were always available, and this successfully bypasses all mitigations that we tested. Even the ones that we found more strict or most resistant to gadgets, so whitelist and nonce-based CSPs. And there's a couple of examples like that. Some of them are, like Sebastian said, more crazy because you need to trigger some tricks in those frameworks. But you can still do that. Like here, I override some private property of the expression parser in Polymer and assign it, well, the window object essentially, right? And then I call the alert function, which is being evaluated against this root data host, which now is a window. So yes, we just call alert here. Or for example, in Angular, well, this one is kind of popular. The Angular JS bypasses are pretty known. So again, we just take the event object and then get the reference to the window and then just call the alert on this window. And what is important here, like Angular makes it invisible sort of to the mitigations because it does reparse the whole thing and executes it on our behalf, let's say. And you can, again, chain those gadgets into making something way more powerful or to execute arbitrary scripts because alert is too simple, right? So here, for example, I overwrite the factory arguments, the first factory argument with a string script. So I try to convince the factory function being called the next time to create a script element instead of whatever it was supposed to create. And then I just call this factory function and assign the result, so a new script element, to the script property here of this particular div element. Then I kind of traverse here and set the source element of this script to data alert 1. So this is a data URL that will alert when loaded as a script. Then I do some reference and essentially set up a me reference to this particular div. Then I call the insert function, or sorry, I set the insert property to the reference of the append child function. And then I call the insert function because I needed that trick, for example, to overcome the limitations of the expression language here, because I can only call functions function by literals. I cannot like do the dots to resolve a given function, right? So I call the append child function on the script element, which will basically create a new element by passing, for example, the strict dynamic CSP. What we found out is we can also steal nonces, which is an interesting attack because stealing nonces was a target of a very interesting research late last year, in which Sebastian and Eduardo found a couple of ways of stealing the nonces from CSP policies or in the DOM that were supposed to prevent script execution using browser queries. And those are slowly being addressed by the browsers, but this is a way of stealing the nonce by just getting the property of a script, of a legitimate script from the application, and then just creating a new script with this nonce, with the correct nonce value in order to bypass the nonce-based CSP. And this is a functionality of a reactive framework, for example. So we have identified ways of bypassing various kinds of mitigations using the script gadgets and chaining them. And we have some tips for you of how to achieve that, right? So if you want to use gadgets to bypass XSS filters or web application firewalls, well, the obvious trick is just encode the payloads. Like even the expression languages give you various ways of representing the very same expressions in different ways. You can also confuse the parser, or a trick that we often used was to externalize the payload. So the actual alert or whatever we wanted to execute was part of the window name reference, and we simply just sort of bound to it. This was, by the way, a regression in no scripts. So client-side sanitizers, that's relatively easy to bypass. You just need to work with a framework that uses, say, benign attributes like data attributes or some whitelisted element types. Like this was the weakness that we found in the default setting of DOM Purify, for example, because it lets through the data attributes, and a lot of frameworks use data attributes and turn them into code effectively. If you have an unsafe eval, just try to find a gadget chain that takes something from the DOM and passes it to eval, sometimes through, say, the jQuery function or jQuery HTML function, for example. For the script dynamic, you have a very similar target or very similar approach. You just, instead of eval, you want to create element script. And again, jQuery lets you do that. There's various tricks of making jQuery HTML function create script elements dynamically. And for whitelist nonce hash-based CSPs, just try to look for working gadget chains in frameworks with custom expression parsers. This is the way that we found is the most successful one. All right, and now I will head back to Sebastian for the overall results. Or not, okay, I will do this section again. So overall results, how common are the gadget chains? This is the question that we ask, and how effective are they in bypassing XSS mitigations? Well, we found bypass chains for every mitigation that we tested with varying success rate, right? What we found interesting is that whitelist-based CSPs and nonce-based CSPs were the strongest to bypass. There's some caveats to it that I will speak about in a moment. But surprisingly, both unsafe eval and strict dynamic versions of the CSP policies, were really bypassable via gadgets in a lot of cases. That's solely because they relaxed the content security policy into being more approachable or more easily so that you can install the CSP more easily on your website, essentially. And especially when combined, this resulted in a lot of bypasses using gadgets. What we also found is some of the results are kind of artificial in a way. So mitigations that overdo their job, so are false negative prone, so will block even if there is no XSS payload in, say, the request. They do perform better, right? But this is the obvious case of like blocking everything. Yes, will stop all the vulnerabilities, but that's probably not the correct approach. And this is, for example, the case for the Edge versus Chrome XSS filter. This one tends to be more permissive, so it allows more gadgets in the end, while Edge is very panicky. It blocks a lot of things that would not be XSS in the first place. This is the whole table. So you can see which framework and which mitigation we were effectively able to bypass and which were sort of immune to that problem. You can take screenshots of that or take photos, but we are also open sourcing this whole research. So there's no much point into talking about this table more. The POCs are here. We just made the repository on GitHub with all the working chains. Well, not for NoScript, because NoScript just updated all of them. So, yep, we bypassed over half of the combinations, essentially. Surprisingly, we did not find any working chains in React, so kudos. And Ember.js was also pretty good because Ember.js in the default mode or in the production mode precompiles the template. So you have no way of actually supplying arbitrary expressions in the DOM because Ember would simply ignore them. And what is surprising is XSS in Aurelia, Angular, Polymer can bypass all the mitigations using the expression parser tricks. Now, there are some caveats to that, right? So this research alone cannot be or should not be used to compare the mitigations between themselves, solely because we only evaluated one aspect, which is bypassability via script gadgets. Mitigations on their own have way more properties, and the decision on whether to implement a mitigation or use it should also take those into consideration, like the deployment costs, performance, or updatability, or in the end, vulnerability to regular plain 10 years old XSSs. Also, obviously, you should not use the framework that has less gadgets or no gadgets unconditionally, right? There's other considerations to take into account. There are some problematic things with us using the default settings, which came out with, for example, when discussing this thing with Mario Heydrich, who did the DOM Purify. And there is a setting, for example, for DOM Purify that will stop some of the gadgets. It's called Save for Templates, so go look into it. We decided to just use the default setting for every mitigation to have some sort of comparable results. And the user-learned code was necessary in some instances, but the code that we used actually to trigger the gadgets, we think it reasonably exists in a real-world application. So, like, for example, we used like the very basic jQuery function in one of the instances. And now I will go back to Sebastian to give you some sort of summary.
Okay, summary and conclusion. I think we need to hurry a bit because time is running out. So summary, what we've showed you is that XSS mitigations work by blocking attacks, not preventing the vulnerabilities, and that we can use script gadgets to bypass these mitigations. And what we found out through our manual study is that gadgets are very prevalent in modern JavaScript libraries. So the problem here is that XSS mitigations are not very well aligned with the web today. So most of the mitigations have been built with the mindset of like applications 10 years ago with a classical reflected XSS, but not with modern JavaScript libraries that have like all these expression languages and so on. So, and we personally consider this as a game changer in mitigations, because I think we've shown that mitigations are problematic and we need to change some, I don't know, some priorities. In some ways we create mitigations. And in this research, we only looked at frameworks, right? And you can say our study is quite small scale, 16 frameworks, that's probably not what's out there. So we're currently preparing a study, actually the crawlers finished yesterday, of the Alexa top 5,000 websites, and we built a tool chain to detect gadgets in user-land code. And we don't have full results yet. We will present results later this year at Black Hat, and we also write a paper where we'll present more numbers. But just a sneak peek, so in these 5,000 pages, we crawled the first level links, which results in around 700,000 pages. We found more than 3 million data flows from the DOM into security sensitive functions. So, and we already found a lot of gadgets through this. So many of these data flows, we have still lots of duplicates, and if we are very conservative, we will still end up with tens of thousands, or thousands or tens of thousands of gadgets in the Alexa top 5,000 web pages. So what do we do about it? We have different strategies, and I will talk about three. So the first way we could deal with this is adding gadget awareness to mitigations, and this is already what's happening, right? NoScript, for example, blocks all the gadgets that we found nowadays, but it's kind of an incomplete fix. It's problematic because in a mitigation you probably cannot cover all the different expression languages and all the different ways you can execute code through gadgets. And also, we have the problems of false positives. As soon as you are starting to overcatch and try to identify everything that might be a gadget, you might run into cases. And there's already one in DOM Purify with another feature that is addressing something similar to gadgets. The second approach that you can take is patching gadgets in frameworks. So remove them from the frameworks. And I think while it is possible, it can be difficult in practice. So because we just have so many different libraries and you need to patch all of them, we found gadgets in all of them, except for React, because of the special way they handle the DOM. But also gadgets are hard to find, right? So some are very easy to find. Right now it's very easy because nobody ever looked at it. But I would say a gadget is as hard to find as an XSS flaw. So basically the problem of finding all the gadgets and fixing all the gadgets at scale might be as difficult as fixing XSS, which we haven't achieved yet, right? So, and sometimes the gadgets are just features, right? We can remove expression parsers and get rid of gadgets, but then we don't have expressions anymore, right? So most of the developers will probably push back if you send them a patch because it's not a direct bug. It only turns into a bug if you have a mitigation and another XSS combined with it. So we believe in another way. And I think one of the key problems of the web or of XSS today is that, let's say you have a novice programmer and you give this programmer a task to write a complex application. Will it be secure? And I think we all know the answer, no. It will never be secure. It will be full of bugs. And that's a huge problem. And the task is not getting easier, it's getting harder because applications are getting more complex. And that's why we think we need to move to a secure by default direction. So we need to harden the platform. We need to provide the tools that a novice programmer that has never learned about security is not able to introduce XSS. And we can do that, for example, by providing safe APIs, by removing all the old cruft like inner HTML and document write from the browsers and replace them with safe templating systems and so on. So we need better browser primitives. We need also better build time security. For example, some frameworks are pretty good. They're compiling their templates at compile time. So there's a compiler before you deploy the framework. And that gives you some nice security properties that you can check before you actually compile. And we also need better isolation primitives. So that's something that we see in the binary world. It seems in the binary world, mitigations are also kind of problematic, like data execution prevention or ASLR. But what works well is isolation techniques, like sandboxing techniques. And we already have a couple of these isolation techniques in the browser. For example, suborigins, iframe sandbox, or there's another proposal of Eduardo, which is called isolated scripts. So I think we should look into those. And for example, iframe sandbox is pretty solid. If you just put user input into iframe sandbox, even if there is an XSS in the sandbox, there's nothing the XSS can do. I think we should shift our focus to hardening the DOM and creating these isolation primitives in the future. And with this, we would like to thank you for your attention and feel free to ask any questions that you might have. No questions?
Yes. There was no gadget chain in Angular 2 because it precompiles the templates. Is that what you're saying?
No, so we haven't looked at Angular 2 in this research, but we looked at React, and React didn't have any gadgets because they have a very special way of handling the DOM interactions. So usually frameworks read from the DOM, like all the templates are in the DOM, and then they are written back to the DOM, right? So you read and write, and React takes a different approach. So in React, you can write your templates directly in your JavaScript file. You just really write HTML in, and you compile the JavaScript files. So the template from the JavaScript file is turned into a piece of JavaScript by the compiler, and they never read from the DOM. They always only write from the DOM, write to the DOM. So there is the template. Whenever you update it, it will be rewritten and updated. So you only have a write flow, but never a read flow. But they can only achieve this because they have pre-compiling. So you couldn't do this functionality in like a standard JavaScript thing today.
Hi, a question about Angular 1 specifically. Would you say it suffices to simply avoid injection before Angular is running? So is Angular capable of sanitizing these things itself?
Yes. So when the Angular bootstraps, it basically treats a subset of it of the DOM as the template, right? And it executes all the expressions from it. So yes, in theory, if you prevented XSS's pre-bootstrap, then you would have a secure, let's say, a basic Angular application would be secure in that case. However, first of all, yes, we cannot fix XSSs. That turns out to be a very prevalent problem of the web. Even if you have, say, I don't know, server-side injection, in the sense that like a regular reflected XSS, that is being sanitized on a server side, this would still be a problem for Angular. But second of all, what is important in practice, a lot of Angular applications, especially I'm talking about Angular 1 applications, they compile templates at runtime. Like in the Angular directive, they do $parse or $compile, again, taking data from the DOM and doing some sort of like a double interpolation on dynamic template compilations. And if that part of data, even injected post-bootstrap, was tampered with, right, was a result of the injection, then you have the original problem.
Okay, thank you very much.